This video is about the embedded Linux toolchain. So we're going to understand the components of an embedded Linux toolchain, understand how to set one up, and understand what we mean by toolchain sysroot. And this will all be useful for your assignment 2 implementation. So when we talk about a toolchain, what we really mean is a combination of a bunch of different components, including the compiler, the linker, and the runtime libraries. So there are two popular options that the book discusses as likely toolchain options, GCC and Clang. And we're going to go over and cover GCC in this book, and we'll use that as part of assignments 2 and later. So some of the components of the GCC toolchain, there's bin utils, which is really the binary utilities. And so those are including the assembler and the linker, the components that make up the compiler applications. And then there's GCC itself, which is an abbreviation for GNU Compiler Collection. And this is the compiler that supports different programming languages. And in our case, we'll be using the C version of this compiler. And then the other part of the toolchain that we'll be using is the C library. And this is going to be using POSIX definitions to have API implementations that we'll access from our program. So ways for us to get into and out of the Linux kernel through that API defined by POSIX. So there are a couple different options the book goes over for setting up a toolchain. Number one, you can do it manually by downloading, building, and installing all the components yourself. And option two is to use a build system to generate it. And this is part of what we'll talk about later in the course with Buildroot and Yocto. So why would you want to hand download and build your own toolchain? Well, there are cases where it might be useful to do this. In general, though, if you're talking about building an embedded system project and you're able to leverage one of the frameworks we're going to talk about later, like Buildroot and Yocto, you probably don't need to do this step. So the reason we're going to do it with assignment 2 is just to understand and kind of demystify the process. Understand more about what these tools are going to be doing for us. So there's two different types of tool chains that are discussed in the book. One is the native tool chain, and the native tool chain is going to run on the same system as the program it generates. And then there's a cross tool chain. So in a case of a cross tool chain, you're going to ultimately run the executable you generate on a different architecture than the host. And so this is what's referred to as cross-compiling. And this is what we'll be doing for this course. So typically we'll be building on a Intel x86 machine, but we'll be compiling and building for an ARM-based target. So the output that we generate from our compile step won't actually run on our host machine. It'll be built specifically for an ARM target. While the applications that we're running, GCC for instance, those obviously need to run on our host machine in order to do the compile step. So that's what we refer to when we mean that's what we mean when we say cross-compiling. So why would you use a cross tool chain? There's a couple different reasons the book goes into, but in general, your host is probably going to be more powerful than your target. And so your builds are probably going to be faster to build from your host machine. And you probably also don't want to have the image that you use for your embedded target. You probably don't need all of your development tools hosted there. So there's probably no reason to necessarily to ship a full compiler with your embedded device. And maybe you don't even have the space to fit that in your device to begin with. So having this cross-compile set up from our host means that we have the option to use the most likely additional resources of the host compared to the target to have this a compile setup that's going to give us additional performance or have additional space to store programs that we don't actually need on the target for shipment of an embedded device. So in terms of the way you specify a cross-compile target, there's a specific syntax for GNU where a prefix to the command that you're trying to invoke, in this case GCC, specifies what you're trying to cross-compile for. So example of the QEMU system that we're going to target with assignment 2 and later is what's called AArch64 or the ARM 64-bit architecture. And an example command line that you'll see for your toolchain target is something like this: AArch64 none Linux GNU GCC. What you can see here is this last GCC part. This is the part you're familiar with, right, as a part of just normally native compiling an application for a host. And all this prefix that gets appended onto the beginning of it is all about telling the identifying what you're compiling for. And so the CPU here at the beginning, AArch64, indicates that we're compiling for ARM 64-bit. The vendor is none. Maybe if there was a specific vendor that we were targeting here instead of just a generic QEMU machine, there might be a specific vendor for the CPU listed here. The kernel type is Linux because we're targeting a Linux kernel. And then the operating system support here is the GNU GCC last step here. So the instructions for building a toolchain with ARM cross compiler are linked to this page that you can find in the reference material associated with the slide deck. And this will change from semester to semester, but what we're really doing here is going out to the ARM website. We're pulling out the precompiled binaries for Linux, and we're just using those precompiled binaries to implement our toolchain. And this is the same thing that the build root framework will do as well. So these instructions might change in terms of version from year to year, but that's generally the format that we'll follow with the steps here. So once you do those steps, what you should see is that you can export append a path to your path variable that will point to the binary directory where these tools were installed. And once you do that, you should be able to run that command that I showed previously, AArch64 none Linux GNU GCC -G. So this part is essentially the same thing you do if you were cross-compiling, and you'll generate that .o file just like you would if you were compiling natively. And what you notice if you run the file utility is that the output's going to say, rather than say that it's built for your host machine, you can see this one's built for ARM AArch64. So this will tell you that you've got a working cross-compiler for AArch64 that's able to cross-compile a C file. The other thing to know when we're talking about cross-compiling and toolchains is that the toolchain is going to be dependent on what's called a sysroot that'll be installed as a part of the toolchain installation. And one way you can see your sysroot path is to use this GCC command with the -print -sysroot option. And this is going to show you a path to a location on your host file system where the sysroot is installed. And what the sysroot is really the root file system of that cross toolchain. So the files that are going to be in this are all specific to the target type. So if we're compiling for an AArch64 type, the files that are located in this directory are all going to be the content that would be on the host root file system if we were compiling natively. But instead of being binary files that are intended for the host, they'll be the binary files for the target, in this case, AArch64. So for instance, if there's libraries you need to link to as a part of your application, those libraries would be located here in the sysroot directory. So this libc library is a library that we'd link to in order to access those POSIX APIs that I mentioned before. And this file will be compiled for the AArch64 target. And some of the files, are going to be needed to compile programs, and other of those files are going to need to be installed on the target at runtime. So some of the different directories in your sysroot, the lib directory is going to be the shared objects for the C library, and so this is content that's going to need to be installed on target. The user lib directory is for static library archive files, so this is used as a part of the C library compile steps. And user include is where the header files are going to be. So when you do stdio.h, this is where that file is going to map to when you're cross-compiling. And then user sbin is where the utility programs for the cross toolchain would be located. So this would be as a part of your build step or after to analyze the output of your build. If you need to run host tools that know how to analyze ARM executables, this is where those files will be located in your sysroot. So what do we mean when we say we're going to have runtime target files? So files that are located on your target at runtime. So if I use the the example here of a path to a .so shared library file, and I use the file command to look at the content of that file. What I see here is, once again, that this is an ARM AH64 library. So this is a library that's not going to be used or useful for my x86 host that I'm using for compiling. It's really going to be specific to the toolchain, and it's going to ultimately be installed on the target. And this will be the case even when it's built on a different architecture. So even though I'm building from x86, this particular file is the file that goes on my target when I'm running on an AH64 based system. So will the AH64 None Linux GNU GCC compiler be in the sysrut? And the answer is no, it won't be in the sysrut, and the reason is because we're cross-compiling. So this one is in your host system file system. It's run by your host system because it's a part of the compile step that you'd run for your host machine. Some of the other tools that are going to be located in the tool chain are going to be GCC and G++, so the different compiler types. So this would be the one you'd use for C++. GDB, so your cross debugger would be located here, and LD would be your cross linker. There's also a few other utilities the book goes over. Adder2line can convert the program address into file names and numbers for debug, and objdump or objdump. We'll get into this one in a later assignment, but this is useful for taking an object file and relating the content of an output object file to associated source code. Strip is another one that's going to be used for us by default in some of our later when we're getting into application build tools like Buildroot and Yocto. And this is going to remove debugging information from executables and make your binary files smaller so that they'll use less space on target. There's also a readelf utility that's going to just have additional information about executables, like location and memory map, for instance. So one other concept to understand when we're talking about cross-compiling and tool chains is static versus dynamic linking. So GCC or G++, as I mentioned before, we're going to be invoking POSIX APIs, and the way we'll do that with GCC or G++ is using glibc, which is the GCC version of the C library. There's two different options about how you would link with GCC. One is using static linkage, and in static linkage, all of the dependencies, so everything that you need from glibc would be pulled out of that archive and placed directly in your executable. And this is contrasted with dynamic linking, where in dynamic linking, your executable doesn't actually have that content of the glibc library. Instead, at runtime, it needs to know where it can find a copy of that code locally, and when it's loaded into memory, the content that it needs from that library will also be accessible. So the benefit being here that you don't need a separate copy on disk for every application that uses glibc, which pretty much every application is going to use. They can all use one shared file that's located in one spot on the file system, not need to duplicate that content on disk. So if you have a way to reduce the usage of file system space through dynamic linking, then why would you ever want to use static linking? Well, one reason that you might want to use static linking is when you have relatively few applications, or maybe if you have only a single application in your embedded system implementation. And you might say, well, that seems unlikely that you'd only have a single application. But it turns out there's a really useful tool that we're going to be using a lot in this course called BusyBox, that it does exactly that. It's just a single application that includes a whole bunch of useful Linux command line functions all compiled into one single application. So if you only have a single application, there's really less benefit to using dynamic linking because you can just include the content directly in the executable. And the second reason you might want to use static linkage would be if you need to run an application before the root file system is available. So when would you not have the full root file system available? Typically that would happen if you were booting up the device and maybe you weren't able to access the root file system content because it was stored on some other device that needed specific drivers to access it. So we'll talk about this more in later versions of the course as well, but you'd be able to do this through a small program that ran at boot that didn't have access to the full root file system yet, but allowed you to start some applications that would give you access and load the appropriate drivers. And in that case, those applications would need to be static linked since the full root file system content is not yet available. So in this slide, I'm showing some commands that are useful for understanding some of what we're going to be covering in assignment 2 and 3 in terms of the use of shared libraries and dynamic linking with an application. So what I'm showing here, we're using the Finder app that you'll implement with assignment 2 and assignment 3. And really, it's the same application that you implemented as a part of assignment 1 with shell scripts. But we're going to be building an application here using a cross-compile prefix. And so you can see here that this cross-compile prefix that I'm specifying is just exactly that prefix on the GCC executable that we talked about before that specifies your toolchain. So I'm specifying this cross-compile prefix, I'm doing a clean, and I'm removing everything. I specify the same cross-compile prefix, and I use the all target to build my application. And so you can see what this is doing is running GCC just like you would from native, but prefixing it with what I specified for cross-compile, and generating an application that is going to be cross-compiled for my AArch64 target. If I then use that readelf utility to look for information about the writer application and look for specifically for grep for shared library, what I can see here is that it's using the libc.so.6 shared library. So this is going to need to be on the file system of the target in order for my application to run successfully. And if I look at the program interpreter, this would be a second reference to a library that I'm going to need in order to run my application on the target. So if I use the same readelf utility and look for the requirements of the writer application, and then grep this for a program interpreter, I can see here that there's a reference to lib ld-linux arch64.so. These values might change depending on what version you have, but this general pattern here should allow you to find the necessary files that you're going to need on target in order to run your application. So why is the ld-linux arch64 listed here? This is really one of the shared libraries that's going to be referenced by a writer. And what does it mean that libc is listed here? This is the file that needs to be available on the root file system to run that writer successfully. So both of these files are going to need to be located on your target in order to run your application. So where would these be located? The linker is going to check for shared libraries in lib64, userlib, or userlib64. There's also a ld library path environment variable that you can set to specify other locations. But for our purposes, you'll follow the details in the assignment. This will be mostly relevant when you get to assignment 3, but you'll want to make sure that your lib and lib64 directories are set up with the appropriate content to run your application.